Well, hello, everyone. Welcome to Cutting Edge Digital Manufacturing Part 2. I'm John Hornick, the Chief Strategy and Communications Officer for Nscript, based in Orlando, Florida, and author of the book, 3D Printing Will Rock the World. This is Part 2 of a two-part webinar. Part 1 is available on the Nscript website, also on YouTube. Manufacturing Part. Echo, Brenda? Okay. Can you hear me okay? We hope everyone is safe and healthy. We are excited to get a great turnout today. Am I still on, Brandon?
Yes.
Okay, I lost the screen there for a second. Sorry, just a couple technical difficulties. So we just have a couple ground rules today. We're going to take all the questions at the end. Each speaker will have 15 minutes, and LJ and I will give them each 2-minute warning and then a time's up warning. We should have about 30 minutes for questions at the end. All the questions are going to be by the Q&A feature on the Zoom platform, and the audience is going to be muted. Please feel free to address your question to a particular speaker if you like, or to the whole panel. Now my colleague, LJ Holmes, will introduce the first speaker. Hope you enjoy the webinar.
Hello, everyone. Today, leading off is Dr. Eric Waxman is the director of the Maryland Energy Innovation Institute and the William L. Krentz Centennial Chair in Energy Research at the University of Maryland in College Park. Eric received his bachelor's in chemical engineering from UC Berkeley and his PhD in material science and engineering from Stanford. He is the vice president and fellow of the Electrochemical Society and a fellow of the American Ceramic Society. His research is focused on ion conductivity materials and electrocatalysts, where he has more than 270 publications, 24 patents, with 3 companies having been founded around his technologies. It's my pleasure to introduce Dr. Eric Waxman.
Thank you very much. Appreciate the wonderful introduction. I guess I have to do this share screen thing here, so bear with me a minute. And hopefully everybody can now see my slides.
Yep, good to go.
So I'm going to talk about the work we're doing in solid state batteries, particularly 3D printed batteries. And of course, you know, the basic technology is that you have a print head and you scan around and create a structure as shown here. We are using the Nscript 3D printer because I work with ceramic materials, and the ability to use a slurry or paste is quite convenient for that type of technology. It results in printing of things that are closer to near net shape, less shrinkage, et cetera, because we typically have to go through a firing step. So the basic process is shown here. You have the various different layers. We printed on a substrate. LLZ is a lithium lanthanum zirconate. It is a garnet type material. And it is an ion conductor. And to kind of give you information about what that material is and why we do it, this is from an interview I had in CBS this morning about all the battery fires. If you remember poor Samsung, when they had their phones caught on fire, they had like a $7 billion capitalization loss. All batteries today are made with an organic liquid electrolyte, which basically is very flammable. And you just saw the flame as it completely burned out on the video to the left. The video to the right was this ceramic garnet material. We held under the same flame, and all you saw is some soot deposition from the flame itself. We fire these things at around 1100 degrees centigrade. So very unlikely your phone's going to catch on fire with this type of material. In fact, it thermodynamically couldn't. The other aspect of these materials, which are quite good, is that they have a high conductivity, and then that's the plot to the left, comparable to some of the organic electrolytes on the order about 1 millisiemens per centimeter. And they also have very high voltage stability. And so that's the plot to the right of that, that's going from sort of 0 volts relative to lithium metal. And I'll come back to why the lithium metal aspect of it, and well over 6 volts. And so as far a range of cathode materials or battery configurations that there are known in the world, this particular material is thermodynamically stable in contact with it, and again has the conductivity that's comparable to some of the conventional electrolytes. They're made from relatively inexpensive elements, lanthanum and zirconium. Some of the dopants can be, more expensive, but they're in a small quantity. And of course, there's lithium, but of course, if you're gonna have a lithium battery, you're gonna have lithium. So that's no worse than any other. But the aspect of this, which has made these quite attractive besides the safety, is the fact that they're stable to lithium metal. And the battery world is trying to get towards a lithium metal anode because basically that will increase the capacity of your anode on your battery by about a factor of 10 relative to conventional carbon-based anodes. The problem with a liquid or polymer electrolyte is these things called dendrites form. And you see that in the SEM photograph to the left, and those will go through from the cathode to the anode, from the anode to the cathode, and create a short, causing your battery to overheat and potentially explode. In contrast, there's a SEM image there of lithium metal inside some of the pores we have in our ceramic electrolyte. It's quite stable and allows us to cycle lithium metal and then therefore use lithium metal as an anode, which is much higher, as I said, capacity and therefore energy density out of our batteries. So the basic process, like I said, is we scan a printing capillary around using the 3D printer as shown here. You can read more about it in this advanced materials paper we published. The first step is to synthesize your ion conducting ceramic, again, in this case, garnet, and there's the composition of one of them. They have to be sort of sub-micron size, and so you can see a volume percent versus size plot there, and an SEM image of some of the powders. So they're on the hundreds of nanometer scale type range that allows them to flow through the capillary on the 3D printer. You've got to develop the ink compositions with the optimum printing rheology. And so you see the shear stress versus shear rate on the left, and then sort of an example of what that does. So those are two different prints, and they're held at a 50-degree angle. The one is a self-supporting ink, which has the higher shear stress, maintains its structure, it doesn't flip over, whereas the conformal ink has too low of a shear stress and it just flows and runs down. So we want to have something that's self-supporting because we want to make these vertically aligned structures. Again, with these types of ceramics, we would then follow that by a drying and sintering step. And I'm not going to go into more detail about that, but typically they are sintered at around, as I said, 1,000 to 1,100 degrees centigrade. This is just showing you the printing, again, using the camera in the in-script printer. These are column structures, and basically put in a CAD design, and it scans through and prints these column structures, which I will show you more of in a few minutes. So there's a number of different structures we can make. This is one, this is what we call a tri-layer. It has a porous, dense, and porous layered structure. What we're doing in our batteries is we're filling the porous structure with the electrode materials, lithium metal on one side and whatever the cathode may be on the other. And you want that separator layer to be dense to prevent the shorts between the two different layers. We also make bilayers, where again, we have a thin, dense film that's supported on a porous layer. And we've even been able to make self-supporting dense films on the order about 5 to 10 microns using these types of materials. However, most of our work has been towards making electrode structures. So we want a dense layer for the center of this thing, but we want to control the architecture on the different electrode surfaces. And so we make a number of different structures. These are lines here. And so again, they're printed. You can see the SEM image here. We're now filling this thing with a cathode material. We can measure the impedance of that. And these are the arcs from the electrochemical impedance spectroscopy. And this is a plot of the reduction in interfacial area specific resistance versus the increase of the surface area. So the figure to the upper left is just a smooth disc of the garnet. And you can see as we increase the surface area of this 3D printed garnet on top of it, going to lines and then ultimately to grids, that the area specific resistance drops linearly with the increase in surface area. So as you increase surface area, resistance decreases, and there's a direct linear relation to it. And that's again why you want to make these types of structures, because you want to reduce the resistance of the cell because if you reduce the resistance of the cell, you increase the power that you can pull out of it, the charging rate or discharging rate of the battery. We made a number of different structures, and so this is one of the ones here. This is a grid structure. What we've done is we make that bilayer. If you remember, I showed you that to you before. That's on the bottom of the cell. That's what we're using typically for putting lithium metal in, and then we put the cathode material in the grids. And again, these are just grids back and forth. You can see the as printed photographs on top and the sintered structures below. We can make these on the order about 100 microns high of this lithium, lanthanum, zirconium, garnet type material. In terms of sort of lithium cycling as an example of the electrochemical characterization we've done, again, we can melt lithium. It fills the pores of the ceramic. You can see conceptually on the left with A, an actual SEM image on the right with B. And then the data below C is the cycling data. So we're basically cycling lithium back and forth at room temperature between the two sides of this structure, achieving 0.1 milliamps per square centimeter, 0.33 milliamps per square centimeter, et cetera. And there's a sort of a blow up on there. You can see the square wave as basically these symmetric cells cycle lithium back and forth between the two sides. And we're literally cycling, tens of microns of lithium metal at room temperature on every cycle. So it's a lot of lithium if you really think about it. They can cycle back and forth because of the high conductivity of these garnet materials. And moreover, the impedance of these things is very low, again, because of the high conductivity of the material, but also because its extended three-dimensional structure allows for high surface area. This is another structure we made. These are columns. And so again, you can see sort of the graphical representation on the left, and then the as printed photograph, and then moreover, the SEM images of these sintered structures. And you can see they're about 200 microns in height, very uniform across that surface. And so again, now what we're going to do is we're going to fill them with a cathode material that we'd use in batteries. NMC is a nickel manganese cobalt material. It's very common in batteries. It's one of the more higher performing ones. So again, you can see the columns to the left, the photograph just to the right of that shows you the garnet columns on that bilayer structure, and then the NMC cathode, which is mixed with a gel in the pore space between the columns. There's a magnification of that to the right of that. And then the figure to the far right is just looking down on this. And you can see the bumps sticking up from each of the columns as we fill this thing with this NMC cathode material. This is some of the electrochemical performance data at room temperature. I'm not familiar with impedance, but this is a plot of the imaginary versus real impedance on the left in figure A there. So basically, we deal with impedance because it has both a resistive and a capacitive component to it. If it was just a simple, metal, then it would just be a resistance. And of course, the resistance and therefore the impedance decreases as the temperature goes up. So you see room temperature cycling and 60-degree cycling. The figure to the right of that is then the capacity that we're able to get out of the battery with every cycle. And the data to the far right is actually the current voltage behavior. So each one of those red lines is a charge discharge profile of this all solid state battery, cycling at 1, 5, 10, and 13 cycles at different current densities. And so the data in the middle is the capacity that we get out of this on the discharge cycle. That would be the curve going down. That's how much capacity we're able to get out of it per gram of cathode material. And as you go to higher current densities, which would be, for instance, the 30 milliamps per gram versus 10 milliamps per gram, you get less capacity. This is very typical for batteries. So you have a trade-off in energy versus power. So at high cycle rates, you get more power, but you don't get as much energy because you're cycling at a faster rate. Okay. And we're also then trying to use this to model what the performance of these types of cells should be and be able to predict what the optimum architecture would be. So the advantage, again, with having very controlled structures is we can then develop transport models to try and calculate what the performance of the battery would be. The figure to the left would kind of give you, again, an example of these columns of cathodes. We have the parameters of the diameter, the distance between columns and things of that nature. The red line's there to indicate the lithium flux that would occur. And the data to the right is actually then cycling data using the models as the lithium cycles back and forth between anode and cathode. These models we're developing can be applied to any 3D framework, including grid, column, and random porous type structures. They also give us some indication of what type of feature sizes we want to have. And so these are plots of the electrode utilization, how much of the lithium material in the electrode, which is filling the space between the columns, would be utilized as a function of time. The faster this goes, the more vertical that line would be, the more power we could get out of the cell. And there's for the grids and column structures, as you see here. And then the different colors there really depends upon what the feature size of that in terms of microns. So, 150 microns is sort of the yellow, and the top one is about 6.25 microns. Clearly, the finer features gives faster rate cycling capability. And that's what's shown on the figure to the right, which is the relative C rate. C rate for a battery is the charge rate, how fast you can charge and discharge it, versus the feature diameter on these grids and column structures are shown there. The other aspect for columns, for grids, is where do you place them? Do they directly overlap each other, or do you have them staggered? And what we're seeing from the modeling results is you actually want to have the grid structures staggered, so that as you have these different lines, that you want to have them overlap in such a way that one line overlaps the pore on the layer below. And then ultimately, we want to be able to calculate what type of energy density we would get. And so this is for lithium sulfur cells that we've been making, not 3D printed, but actually made using conventional tape casting and laminating and firing. We're making these types of lithium sulfur cells and getting on the order about 280 watt hours per kilogram. If you're familiar with batteries, your best Panasonic is somewhere around 240 or something like that. So it's actually a higher energy density than conventional batteries today. But the thing is that now we have the ability to look at how we tailor the porosity in these structures and how that affects the overall cell energy density. And what we're seeing is that, if we make sort of this all 3D structure type battery, we can potentially get sort of the 940 watt hours per kilogram, about 3-4 times that of conventional batteries that are on the market today. And I think I made my time. I want to thank the postdocs and grad students working in my group, as well as the Department of Energy for its funding. And I thank you for your attention.
That was wonderful. Perfect timing, Eric. Appreciate that. Our next speaker is Dr. Eduardo Rojas. He earned his master's and PhD in electrical engineering from the University of South Florida. He's currently an assistant professor in the Department of Electrical Engineering and Computer Science at Embry-Riddle Aeronautical University, my alma mater. Eduardo's research interests are in the area of microwave and millimeter wave circuits and antenna applications. He is the recipient of the Career Award from NSF and is the director of the Wireless Devices and Electromagnetic Lab at ERAU. He has more than 30 peer-reviewed publications, 4 patents, and multiple patent applications, all in additive manufacturing. It is my pleasure to introduce Dr. Eduardo Rojas.
Well, thank you. Can you hear me well?
Yes, good to go.
Okay. So, well, thank you for the introduction. I'm going to be presenting about additive manufacturing with a focus on aerospace applications of wireless devices. So the work I'm presenting is towards space applications and aviation applications. And I joined Embry-Riddle as you saw in 2017. So the last 3 years we have been putting together a lab with a focus of additive manufacturing for RF circuits and antennas. But before we go into the details of the lab and the research, some motivation for additive manufacturing, I like to show this plot here, where you see the blue line, which is cost versus volume of production. And you see traditionally, if you have a low volume, it's a really high cost. And as you fabricate thousands or millions of devices, the cost goes down, which is typically the model used in the industry. And then you also have the green line, which is cost as function of complexity. So for parts that are, fairly simple, the cost goes lower, but then as you go to more advanced and complicated parts, then the cost goes kind of non-linear, right? So when I say the additive manufacturing opportunity is where you have either low volumes, for example, in prototyping or parts that are for limited volume. You see here, the orange line is the cost of additive manufacturing, which is not dependent necessarily too much on the volume or the complexity of the part. So there is an opportunity when you have low volumes, or you have a part that is very advanced, is highly complex, where traditional manufacturing really would make it not really feasible. Then there you see the value. Now, as the orange line goes down, which is doing, really the region for additive manufacturing keeps growing. Now, there is an old paradigm for engineering and scientists, which is simpler designs are less costly and better. And really, with additive manufacturing, that's not true anymore. Mostly in the sense of making optimized parts that are complex, they are not necessarily more costly to produce. So that's giving an engineer the freedom of opening the mind and looking at novel geometries or novel materials without thinking that this would really never go to the industry. And then again, all this enables the discovery of geometries and materials that are not possible with traditional means, as you already saw in part 1, and you already saw in the previous presentation as well. So the evolution, or perhaps the revolution, is going from a clean room with a controlled environment, advanced multi-billion-dollar equipment and infrastructure, or a machine shop where you get the parts and you do subtractive manufacturing with all this equipment and this large room, to solutions like the Nscript tabletop, where you can additive manufacture using micro dispensing or fused deposition modeling, or also you can do subtractive with for example, a femtosecond laser, all in one system, going from a digital file to a part. So that's really what I call the evolution with additive manufacturing, or digital manufacturing in a more general sense. A little bit about our lab. So we are in Embry-Riddle in the Joe Mica Research Complex. It's a brand new building. As I mentioned, it's only 3 years old. We are here in Daytona Beach. We have a nice weather today. And the lab, we have a 2,000 square feet of RF labs in the second floor right here, when you see in the slides. So things that we have been building since I joined, we have a picosecond LPKF proto laser for PCB manufacturing. We have RF probing, a far field and a quiet chamber for antenna measurements, 12 by 12 by 25 feet. We can do S parameters measurements and signal analyzer measurements up to 67 gigahertz, now covering the millimeter wave frequencies for example, 5G applications. And then we have our Nscript tabletop with a femtosecond laser, among other equipments. Of course, we are an aeronautical university, and we focus heavily on aviation and aerospace and space applications. So we have in the lab a ground station for satellite tracking, actually 2 ground stations, so we can track 2 spacecraft simultaneously, and the frequencies S-band, UHF, and VHF. And I'm going to talk a little bit about a space application shortly. So additive manufacturing, as I mentioned, enables manufacturing things that are not easy or even not possible to do with traditional means. And here's a set of videos of what we do in the lab. So on the left, you will see printing a high permittivity electric ink in permittivity of the order of 30 with a micro dispensing tool on top of a conductive layer, which is in this case equal to 8 DuPont. So you see you can develop multi-layer structures on surfaces. And you can also do it conformally. So you see here is a foam frame of an aircraft that you can print conformally antennas and RF circuits in the second video. And then we use laser, and you see in the third video, for fine features in the order of 10 microns for obtaining those feature sizes of our higher frequencies. For example, millimeter wave, you need to use, you need smaller feature sizes. And as I mentioned, we have a more commercial PKF system for PCBs manufacturing, and also looking at processing of printed parts, so you see in the last video. So as you see in the lab, we use both additive with micro dispensing and fuse deposition molding, but also subtractive with the lasers. So I'm going to be now covering a few of the research initiatives that we have in the lab going on. These ones are funded by NSF and AFRL, and they are related to conformal antennas using novel materials, in this case, high-K inks for miniaturization. And the concept is really going forward and looking at structures where, for example, a UAV, in this case, you have these large surfaces in the wings that are not really used for for anything else other than aerodynamics, just flying. So could you use those surfaces as antennas, for example? So use them for higher gain, for radar sensing, and other applications. So really, additive manufacturing enables printing on top of these surfaces and achieving, for example, multi-beam, multi-frequency antennas on the wings. Here's an example of, you saw the video printing on a UAV wing, a high-K, the electric ink. And there here you can see on the top figure, the surface of the wing, and then on top of it, once you print the ink and you re-scan, this is a scanning of the surface, you can see the layer of the ink there. Also, this is with our collaborator from the Air Force, from AFRL, looking at moving planar antennas to 3D surfaces, conformal surfaces, for example, in radomes. So the advantage of this kind of applications is freeing volume out of the inside of the radome and moving things to outside of the radome. So you can now use that volume for other purposes. So that's really the concept of conformal antennas directly manufactured on the surfaces. Then another initiative, and this is funded by NSF, is by Inspire antennas or geometries, which is again freeing our mind from the traditional engineer that thinks in 2D and going to 3D. We got inspiration on flowers for this one. This is our very first work that we published on looking at a patch antenna and making the pattern wavy. So we effectively increased the electrical size, but the physical size is the same. So then you get miniaturization of the antenna. So you go from this planar patch to a wavy flower-like patch. And you can reduce the operation frequency if you keep the same physical size. In this case, from 5 gigahertz down to roughly 4.5 gigahertz. Or miniaturize the antenna if you keep the same frequency. And here's the measure and simulate areas 1.1 under radiation patterns, just to show that the behavior is very similar. Then we also collaborate with our colleagues from the aerospace engineering department with a lot of space applications. And there is one issue that NASA and the space community is looking at, which is the orbital debris and micrometeorites. And it's really, as we have a lot of debris in the around Earth, so there is a high risk of getting impacts by these micrometeorites or orbital debris. So there is an interest on detecting these impacts and assessing the damage before there is an emergency in the aircraft. So we work with our collaborators on sensors that you can put in these inflatable habitats. And the idea was to make the sensor passive, completely passive and wireless. In other words, you can interrogate the sensor, it doesn't have any battery or any power, and it will transmit the reading of the sensor in terms of impact. And the system is very simple. You have an interrogator, and then on the sensing side, you have a sensing sheet, called a composite sheet, that is connected to a sensory IC with an antenna embedded all into one that you will see. So with this, you leverage additive manufacturing to fabricate a cube, almost a cube. It looks very simple, but every conductive layer feature controls the behavior of the antenna. And we embedded the IC sensing IC into this little cube, which can be then placed next to the sensing patch that you see on the right lower image. And then what you have is every time you get an impact, in other words, you get a hole in the sensing sheet, the resistance of this sheet will change, which is sensed by this passive wireless antenna and IC, and this will send the reading back to the reader. So you see here the test setup. You have the antenna, the PIFA antenna with the IC, and the piezoresistive sensing patch. So as you open a hole here in the reader, you will get that reading of resistance. And the more holes you put, the more resistance you get. So you can detect how many impacts, when did they happen, and also the severity or the size of the impact. We also collaborate with a company called Sensatech, which is in our research park. And also we got funding from NASA on working on a sensor that measures the pressure and temperature on harsh environments. The company Sensatech, they focus on the concept where if you set up an array of sensors, temperature and pressure sensors on blades, on turbines, you really get the health of the turbine. You can detect if some things are degrading, and you can do preventive maintenance as opposed to just getting the whole turbine fail. So that's really the vision of the company, and we working with them on using additive and subtractive manufacturing, which is imprinting patterns with the conductive ink and laser machining cavities and features to fabricate these high temperature and pressure sensors. And you see here examples of the samples we have fabricated with them. And
Eduardo, you got about 2 minutes, Eduardo.
Okay, so I'm gonna move faster then. So we have deployable space antennas. This is with IEEE NTDs challenge, and with a company called Visidos as well from Hawaii, which is looking at origami inspired antennas they can deploy. So here you see ITU CubeSat with our antenna. Here's the stored volume, and here's when it's deployed. We're looking at making them with a traditional manufacturing with drawers, but also with the additive manufacturing. Here you see the comparison of the two. We are working with intuitive machines, which is as well working with NASA and the CLAPS program, or to make a lunar lander that is going to the moon, hopefully next year in the fall. So we're working with them on the wireless systems, both to Earth and on the communication on the lunar surface. And then, unfortunately, I cannot share much details, but we are also working on an experiment, ISS experiments that will launch in October. So this is, I guess, a tease, and we'll share the details in the next part of these seminars in the next edition. And then, I guess the vision is, on Earth, in here, we can discover novel geometries, materials that are enabled by additive manufacturing. So there's the triad there. They are interconnected in the geometries and materials and additive manufacturing processes to advance society. And then from the space point of view, really ad hoc design and manufacturing is an enabler for space exploration. So there's no way you can have a stock of parts and a stock of parts there in space. And if you have a problem and you don't have that part, you have to wait months or years until you get it in space. So the space industry is really focused on additive manufacturing as an enabler of a space exploration. So before closing, I would say I'm very proud of the team here. So they do the work, they make this possible. So we have a team of PhD, masters, and other the students. You see the picture there. So they didn't want to go without saying thank you and acknowledge them their work. So
thanks a lot, Eduardo. I appreciate it.
Thank you.
All right, John. John, you're on mute.
I know. Unmute. Okay. Thanks, LJ, and thanks to our first two speakers. Really interesting work with great potential. I now have the pleasure of introducing Dr. H. Sigmarsson. He's the Gerald Tuma Presidential Professor in the School of Electrical and Computer Engineering Advanced Radar Research Center at the University of Oklahoma. His research focuses on applied electromagnetics, including reconfigurable high-frequency electronics and rapid prototyping. Dr. Sigmarsson is a senior member of the IEEE and has published over 80 journal and conference papers. He'll be speaking today on 3D printing of ceramic circuit boards. Take it away.
All right, let me see about sharing my screen here. Hopefully that made its way properly. Well, thank you for having me here today. I slightly changed the title of this from last time. I was thinking of having it as ceramic circuit boards, but I kind of changed it to multi-chip modules. It's a little bit more relevant to the ceramic side here. So without further ado, I'm just gonna hop right into it. Okay, there we go. Okay, so we've done ceramic multi-chip modules for years and years and years, and low temperature co-fired ceramic is, or LTCC, is basically what we've been using quite a bit for that. And a multi-chip module is basically just a, maybe a fancy way of saying a circuit board with some embedded passives and mounted components on there. It's very well suitable for many things, and there are some benefits, including it has great electrical performance, and it's very stable under very harsh environments and things like that. It does allow for embedded cavities and channels for cooling and this and that, so it's very, very well suited for all kinds of PA applications or power amplifier applications and high temperature environments, and it also can be hermetically sealed, which is actually very useful for many applications. So in general, like LTCC by itself is very well suited for these harsh environments and mechanical stresses. So we'll see them in places like engine bays and on rockets and in tanks, and these places where maybe even traditional circuit boards would start melting or have problems. But there are some problems with LTCC, and we are seeing it kind of lose ground a little bit to laminate processing, and so it is fairly expensive. It does take a lot of time and specialized labor to do something. So, for making hundreds or thousands of parts, it's very, very useful, but for prototyping, it's not really. If you want to make one board, it can be very time consuming and very expensive. So, how can we avoid that? And as I mentioned, there are many of our collaborators are moving away from LTCC into more laminate-based technologies. So the question here, and this is something that we asked quite a few years ago, we started thinking about, is can we actually do prototypes, or can we 3D print, for example, LTCC materials? And so in order to do that, we need several things, and just to emphasize a little bit on the complexity of the LTCC process in general, it requires multiple steps, usually multiple machines. You got to take your parts from machine to machine. You have very specialized labor that can do each one of these steps, and then you have it's overall just a fairly complicated process. So the thought process is, can we somehow utilize some of the evolution of printers, the 3D printers, and we started seeing a lot of multi-material printers. These are just some examples of some fused deposition modeling printers over there, that if we can print multiple filaments or multiple materials at the same time, can we emulate this type of process with ceramics? And well, there are several challenges that we need to overcome, and I just listed them here in no particular order other than just what came to mind. And one of the big problems that we have, or challenges, is materials. So we need multiple materials to create a multi-chip module. We need dielectrics for the substrates. We need conductors for making the interconnects and vias and things like that. We also would want some more advanced materials and other dielectrics, high K materials, and I'll talk a little bit more about the advanced materials here in a later slide. Some of the concerns have to do with the particle sizes of our materials. If we're going to extrude or dispense, we need to be mindful of the particle size. That also dictates our grain structure and things like that, porosity and such. The printing platforms themselves, although with all these low-cost 3D printed FDM printers being widely available, they're potentially just not good enough for doing high frequency, high quality circuits, right? So the current LTCC processing, we're talking about something about 2 to 4 mil lines and spaces, and about 50 to 100 micrometers. And these typical FDM printers might be dealing with maybe 10 mil, 20 mil holes and dispensing capabilities. So we're not going to use a $1,000 printer to make LTCC. We know that. So what do we need? Well, we have a lot of other platforms, and I'll talk about that here in a little bit. One of the major challenges of doing 3D printed ceramics, and this goes a little bit to our first speaker's discussion on drying and sintering. And cracking is a major challenge for 3D printed ceramics and sintered ceramics. And as an example, or for comparison, in traditional processing of LTCC, the tape itself is dried in very well-controlled conditions for a very long time, and there's a reason for that. And the sintering process is also relatively slow. And drying and sintering, it can take a lot of time. So one question we should ask ourselves is it really feasible to try to print these things, from all of these challenges? Should we solve these challenges or not? And as academics, of course, we want to tackle these things, and it gives us something to do, I guess. So what we've done here is we started off with some materials from Heraeus, and we had this powder, this X200 powder that they make tape out of. So we just went and sourced the raw materials from them, got the powder, put that into a liquid suspension that we used the monomer with some dispersant, and we mixed it up pretty nicely. And then we put it in a syringe and we dispensed it, and we were able to create relatively decent sized. So these are about 50 mil thick, if I remember correctly, boards that we made out of this. And so we printed them, and then we sintered them, and we also took just regular LTCC conductor paste, and we printed that on top as well. So in the early investigation of this project, I had a master's student that built a printer, little dispensing printer, using servos from a inkjet printer. So this is actually quite interesting. We just used a pneumatic dispenser with some servos, and we created this little printer that we see here in the middle. And we were able to print both the ceramic suspension, and we were able to print on top of the ceramic suspension the conductor paste, and we fired it all together, and it actually came out quite nice. However, there's problems with the homemade printer is just really not good for doing high accuracy. We had okay accuracy. We had a repeatability of about 10 to 20 micrometers on these lines that we printed. So recently we got an N-script printer, one of these gantry units, and that was allowed through the Air Force. So big thanks to the Air Force through their DURIP program. So we ended up getting a 3DN 300 printer with 4 smart pumps. So we decided to go with 4 smart pumps, and I'll talk a little bit about why we want to be able to do that. It'll become more evident in the next slide. But in general, what we wanted to do is be able to put down 4 suspensions at the same time, so that we can do our substrates with our dielectrics, we can do our connections, and we actually use a different conductor for the via fill. It needs to have a different sintering performance. So we fill vias in between with different material, and then sacrificial carbon, and I'll show that in a little bit why we need that. We also got a variety of these ceramic tips, and we've just ended up getting a whole bunch of them, and so we're experimenting with which suspension works best with what diameter, inner diameter apertures. So these are those kind of things that we're doing. So how do we envision doing this module fabrication? So if we start off with just printing a ground plane, for example. So we're assuming that we're building some kind of a circuit. So we start with just printing our layers, maybe print a conductor layer, and then we would print some ceramic on top of that. So print some LTCC on top of that. And then, here's an example where we would put maybe down a sacrificial carbon layer if we want to create some cavities or channels and such. So we would print some carbon in there, and we continue filling some vias, and then that repeats itself. We just keep building on top of that layer by layer until we end up with a complete part. And then eventually we fire that part, and during the firing process, the purpose of the carbon paste is that it actually does get burnt out quite nicely. So the idea would be that we would create some kind of module like this. This is just a printed TR module, if you will, or transmit receive module, where we end up with having some pockets for some chips. We have some embedded components, inductors, capacitors, so on and so forth. And we have, maybe we print these multi-layer antennas that we build into the board itself. And that would be kind of the ultimate goal, is to build everything into the one thing. Now, when we do stuff like this, we do end up getting a certain amount of surface roughness and things like that. So this is where a platform like the Nscript comes in and could do wonders. Let's assume that we had, for example, we would use the end mill. This is a milling head that can be added to it. And if we were to kind of just smooth out the antenna, for example, we could potentially get a much better performance at these higher frequencies. And surface roughness is going to greatly impact your performance at these higher frequencies. So another project that we worked on with doing LTCC-based or type components was, well, what if we want to use our $1,000 MakerBot, or well, I guess it's more like a $2,000 printer, even though I will say for the record that I did buy that particular MakerBot 2X for $900 used, but so it is a $1,000 printer. But so can we make filaments with ceramics in there and actually create ceramic parts? So first off, we started this with our typical polylactic acid, or our PLA, and the problem with that was that it was just too brittle. We couldn't really get high enough ceramic loading into our plastic parts where we could burn out the PLA and be left with a good enough ceramic matrix that would sinter and not just fracture and turn into dust, so to speak. So we ended up moving away from the PLA and we went into our PETG, and it's way more elastic than the PLA, but we were able to achieve so some 71% filling of powder of this Heraeus X200 powder into a filament, and we were able to use a MakerBot printer to print a part and fire it and get some nice parts out of it. So that was actually quite exciting, being able to print out of a $1,000 printer a ceramic part. So, and this is just a graph there showing the different profiles that we use. We have to slightly adjust our profile for doing the sintering for the PETG. We just needed to do a little bigger dwell for it to remove all the particles and remove it a little bit slower. Okay. So what about other materials? I hinted at doing some more advanced materials a little bit earlier. So it'd be really nice if we could start doing some other materials like ferroelectrics that allow us to do potentially some tunable things. Magnetic materials, ferromagnetics, some piezoelectrics. So if we can start printing things that we can have functional after we're done printing with physical movement, that would be nice. And then there's phase change materials. And phase change materials is basically a family of materials where by doing some thermal excitation and different profiles, you can basically change it from being either an insulator or to a conductor and vice versa. This is, has been a hot topic recently for doing some RF switches. And that's with very good performance, low loss, and good isolation. So
Doctor, you have about 2 minutes, if that's okay.
Yeah, okay. Yeah, I mean, I can speed up a little bit. Anyway, so we created, we took we took the GETE 5050, which is good for getting low loss, and we put that into a monomer as well, and we tried to print that. However, we failed to take into account that GETE actually melts at 725 degrees Celsius, and the LTCC process is about 850, so we ended up evaporating all of our GETE. But still, it's something that we want to be looking at. And it would be pretty cool to be able to print all these different materials, but there are some challenges associated with that, and that would be, how do we deal with these different temperatures? If you're printing a piezo material, for example, you can't sinter that at 850 degrees potentially without destroying the piezo affecting the material. So there are all kinds of considerations that need to be taken into account there. Okay, so if we had a good material to do, if we wanted to build a switch, we could just go with our regular printing process. Now we add a heater paste, so we would do a heater, maybe a tungsten-based paste, and then we would then basically build our PCM or phase change material on top of that, and then fire the structure and end up with something like this. Would be like a typical RF switch, which allows us to either block the energy or pass the energy, which would be really nice. So we made some structures. We got in our early discoveries, we basically have a lot of cracking and voids from the handmade. So we still got to work on that a little bit. So overall, just conclude this real quick. We have made some of these materials, still have some challenges, of course. But you know, with these new platforms, and we're really excited to start using our NScript for this, we have high hopes for building some really cool modules with this. And again, just thanks to the Air Force for the NScript printer, and then to Hoorays for providing us with all these materials. So with that, I'll pass off the baton.
Thank you, Doctor. Thank you. Great presentation. I also have the pleasure of introducing Craig Armiento. He's professor of electrical and computer engineering at the University of Massachusetts Lowell, and founder and co-director of the Raytheon UMass Lowell Research Institute. He's also director of the Printed Electronics Research Collaborative. Professor Armiento transitioned to academia in 2003 after over 20 years of industrial R&D experience at GTE Laboratories, which is now Verizon, and Light Chip Optical Networks, where he led projects on optoelectrical device development, photonic packaging, fiber to the home, and wavelength division multiplexing technology. Dr. Armiento will speak on challenges for printed electronics in the microwave domain. Take it away.
Well, thank you, John. Can you see my slides okay?
Yes, we can.
Terrific. Well, first let me thank NScript for the invitation to come and speak today. I'm here to represent a team of scientists and engineers from University of Massachusetts Lowell and from Raytheon, who were joined together in a joint research institute called the Raytheon UMass Lowell Research Institute, or RURI for short. Our focus is on printed electronics for microwave RF applications. And you'll see on the bottom of this first slide a bit of samples of some of the things we've printed, which I hope to speak about as we go through the talk. So this cartoon is kind of a conceptual drawing of kind of where we want to be. Shows a conformal or flexible substrate with a bunch of RF microwave components printed on it, integrated with bare die. Some are 2D objects like patch antennas and resistors. Some are 3D objects like antenna arrays, and we even want to print a connector, which I'll talk about in a few minutes. So we've developed work on almost all these little piece parts, and we've done some work on integrating them that I'll talk a little bit about in a few minutes. But this is kind of where we're going to integrate active and passive components doing digital manufacturing processes. Just a quick comment about the Raytheon UMass Lowell Research Institute. We stood this up late in 2014. This is a fairly unique partnership between an academic organization and a company. Raytheon is very close to our campus, and so we have a lot of engineers who have offices and work with UML faculty and students. Our projects are funded through some internal IRAD funds at Raytheon, and also some federal funds that you see here on the left, ONR, ARNI, AFRL. We've been also supported by projects with America Makes and Netflix, and more recently we have something going on with the NSA as well for some of the authentication work we're doing. This thing was stood up with the idea of helping Raytheon develop technology to go from these large rigid phased arrays that you see here on the ship in the upper right to something that looks more flexible. So we've been doing this for about 5 years now. And what we did also, shortly after we stood up RURI, is we stood up another organization called the Printed Electronics Research Collaborative, or PERC. And this was an opportunity to build up the supply chain. Raytheon as a system integrator isn't going to develop inks or design tools. So what you see here are our partners through PERC that range from materials companies, printer companies, chip manufacturers, and so on. And the idea is that we at the at Rory and PERC want to work with corporate and government partners to address some of the issues associated with RF microwave printed electronics. So our facility, I'll talk a little bit more about the equipment that we have, but conceptually what we're doing is trying to build on one, we have the entire floor of a building, a relatively new research building, where we do design and simulation. We have all the tools that you can imagine. Typically, we use electromagnetic modeling, kind of like what you see with this waveguide up here. We do a lot of work with materials development and characterization. We like to use commercial materials when they're available. And in many cases, particularly dielectrics, we do a lot of work to characterize those dielectric properties, which need to go back and feed back into our design tools. When we can't get a material available commercially, we develop it ourselves, and I'll show you a few examples of some tunable dielectric materials we've developed and some other types of unique materials. Lots of 2D and 3D printing, which I'll talk about in a minute when I list our equipment, and a lot of microwave RF characterization. So the idea is we loop around and we iterate these designs very quickly. One of the things we do with our students and staff is if you need to know all elements of this process. You cannot do a design in HFSS without understanding the materials and the processing aspects of it and testing. So we like to think we have our students understand the whole scope of the process. So our lab is shown here, various pieces of equipment. Here you see this little video, that's our forehead end script, which we're using for a variety of applications, most notably printing RF connectors and printing interposers for microelectronic packaging. We've got Optimex system, the 5-axis system, so we can print very fine lines on 3D objects. A multitude of 3D printers, including this yellow guy here, a large 5-head 3D printing system, and all the usual ancillary materials, photonic curing, profilometers, and so on. In addition to the modeling tools I mentioned, we have everything that ANSYS makes. All of our students know how to use those tools. We have a fairly complete microwave test lab, including our own anechoic chamber. So a lot of discussions both today and last week about materials, and I'm not going to kind of rehash all over that. But I just want to say that, you know, we're all after better conductors. However, you know, it's even more of an issue, a challenge at these high frequencies where surface roughness and edge acuity is very, very important. One of our biggest challenges is getting good dielectrics that have low loss at the very high frequencies we work at, and good control over thickness. So I'll make some mention of that later. We have a expensive ability to do materials characterization. You can't get dielectric properties of a lot of these inks and materials at high frequencies. The vendor's not going to give them to you, so we measure those. So there's a lot of other things here, including an integration of 3D materials, FDM kinds of materials. And I'll talk a little bit about later on why we want to change the way we do connectors as well. And the last bullet I'll just mention, you know, we're developing new materials for frequency agile systems. We've developed an ink I'll mention later on. It's a ferroelectric material that allows us to tune the dielectric constant of the material. And we're also developing some new materials for applications in technology protection, anti-tamper authentication and stuff like that, which I think is very amenable to the additive world. So material characterization, really 3 general categories in terms of form factors. There are thin films like Kapton and other flexible substrates where you want to measure the dielectric constant loss tangent. There are solid materials, things that we print in an FDM system, like the Nscript system, where if we're building a 3D antenna or a connector, we have to characterize those materials as well. have to be cognizant of the fill factor because that affects the dielectric constant, of course. And then there's inks, which is really a challenge. So we have a process whereby we can create a printed concentric capacitor where we can probe with a ground signal ground probe and characterize the inks. And ultimately, we're after our measurements like this, where we can measure the permittivity and the loss tangent out to 20, 30 gigahertz and so on. So that's what all this is about. These data are really critical to feedback to our models for being able to do the work we do with simulation. Here's an example of some of these things we've pieced together. This was actually done with Raytheon, who was the prime on this American Makes project. And this was a C-band phased array element where we integrated a variety of different printed devices in the microwave region. This happened to be on a Rogers substrate. And what you see here are things like a phase tuner, quadrature couplers, and I'll talk a little bit more about that. We've got some gallium arsenide chips in here where we've interconnected them with a printer, not wire bonds. We have a bandpass filter and antenna all integrated together. So we worked on these elements separately, and then we put them all together on this American Makes project. Just to kind of talk about one of those elements that speaks to the challenges for dielectrics. This is a quadrature coupler. You put an input on the left side, it gets splits out into two and shifted by a 90-degree phase. What's required is you've got these two metallic lines with a dielectric in between. You see a cross section here. The dielectric constant and that thickness has to be well known and controlled to be able to design and fabricate this with a set coupling. And that's a challenge right now, is how do we get these dielectrics deposited in a way that's very controlled. And that's just one of the many challenges of dealing with some of these materials. I mentioned earlier some of the novel materials we've developed. In many RF applications, tunability is important for frequency agility. You'd like to have a varactor or some tunable element of variable capacitor. And we developed an ink that's based on a well-known ferroelectric ceramic, barium strontium titanate, or BST, come up with various formulations of those nanoparticles in an ink. What you can see here are that based on modifying the formulation, the nano size, the particle size, the concentration, and so on, we can formulate this ink with different dielectric constants. You see just three examples here in the green, the red, and the blue being roughly around 55, very high K dielectric at 55. And you can see that these measurements have been made in our lab out to 20 gigahertz. Once you've printed one of these inks, then you also have the option of tuning its dielectric constant with an applied electric field. So what you see here is some tunability results, up to 30% tunability at a half of a gigahertz. As you get the higher frequencies from the blue down to the red and purple, then you diminish the amount of tunability you have at those higher frequencies. So we've done a lot of work with different formulations of this BST, and we've used it to create what's called a frequency selective surface, or FSS, which is basically an electromagnetic filter. And based on the size of these unit cells, you can fix the frequency response of radiation going through that. What we've done is taken the extra step and connected these unit cells with an interdigitated capacitor, which has our tunable dielectric material as the dielectric. And as a result of that, you can see in this photograph here, we have a flexible and tunable FSS structure capped on, whereby changing the voltage across, we can tune the frequency response of this FSS. So again, this is a novel material enabling tunability. that doesn't, it's not available commercially. Another area that we needed was a resistive ink. A lot of the carbon inks we worked with were not easy to control in terms of their consistency and their ability to print with very fine lines. We developed an ink. We basically said, let's take a silver ink and make it worse. Let's make it resistive. And we chose to use this barium strontium titanate as a particle to actually reduce the conductivity and create a resistive ink that we can control. And what you see here is a plot of resistivity for different formulations, AG, BST, 10, 11, and so on. We can get a resistivity about 337 times the resistivity of pure silver ink. Now, in the context of doing this, now we can print this with a fine line on an aerosol jet because it's basically a conductive ink with particles in it. And that's worked out quite well. But in the course of developing this resistive ink, we came up with a formulation now of a particular formula.
You have about 2 minutes, Doctor.
Okay, thanks. It's AGBST, where we can actually print it as a dielectric with the dielectric constant of around 17, use a laser to selectively heat it and convert it to a conductive. So what you see here is a drawing of the ground, signal ground. It's a coplanar waveguide type capacitor. And what you see here is this region I'm pointing at right now has been converted to a conductive material using a laser. So we're using a laser to actually write circuits into a dielectric, converting it to conductive. I'm going to have to go through this quickly. We've done a fair amount of work with interconnecting to bare die. This is some work we did a few years ago. One of our master's thesis students how to connect chips to each other. We've done some work in the third dimension. This is a Vivaldi array we did for ONR with our partner SI2 Technologies, broadband, X-band array of antennas. A lot of interesting challenges to making that. And here you see it in our anechoic chamber. We've also done some work on printed connectors. You've seen these very nice flexible circuits like you see here. It's just a very simple case of a bunch of microwave resonators. What do we do to that? We then attach these SMA COTS connectors, which really with a metal plate in the back because the sample is too thin and too flimsy. And all of a sudden now what was lightweight and flexible is now heavy and rigid. So we decided to develop options for printing connectors. We did it first with a very simple DC. Here's a little printed circuit board with 2 LED chips, 2 parts of the connector I'm showing here. These guys snap into place like Legos, and you've got a DC connector. We've migrated that to the RF world, where we use now 2 sandwich coplanar, grounded coplanar structures. These were printed in our NScript system, printing Ultim, depositing silver nano inks, drilling via. So that fully functional NScript is very useful for making complex 3D structures like this. So in closing, we've got a great team of folks who are both from Raytheon and UMass Lowell. Dr. Mary Herndon is my co-director on the Raytheon side. Professor Alkema Kirtlu is my co-director on the UMass Lowell side. And every one of these folks have incredible contributions in the materials in the RF world. And I think I will end there because I'm sure I've run out of time. Thank you.
All right, thank you, Doctor. Thank you. We're now going to go through some questions that the audience submitted. If you have any other questions that you haven't submitted, please feel free to do so on the Q&A function on the Zoom platform. And Brandon is going to, and as I said before, feel free to address your questions to a particular speaker or to all of the speakers. Now, Brandon Dickerson's going to run through the questions that we have.
Thanks, John. Thank you, gentlemen, for your presentations and all the hard work you guys are doing to changing the future of direct digital manufacturing. You guys are truly rock stars here for NScript and all of us here making and selling these tools. So I'd like to start the questions with Dr. Rojas. My question for you is, I'm sorry, Dr. Waxman, I'd like to start with you, sorry. My question for you is, Why solid state batteries versus conventional liquid electrolyte batteries?
So actually I try to address that in the first slide. In that solid state batteries, one, remove the safety concern of conventional batteries. So conventional batteries have a flammable liquid electrolyte that will catch fire and burn. And there's lots of concern about applications all over the place. You know, you probably were told not to bring your Samsung Galaxy on an airplane, or you know, when you go check, well, not that anybody's flying these days, but if you were, you'd be told not to bring your batteries on the plane. And ceramic solid state batteries are completely non-flammable, so it removes that safety concern. The other aspect of it is because of their ability to use lithium metal, they can in fact have higher energy density than any conventional battery using a liquid electrolyte. And so I showed you results where in fact we've already exceeded the energy density of the best batteries on the market today. And we believe we can get much higher energy density. So greater energy density means you can go, you know, longer, and safety means you don't have to worry about it catching fire. I mean, those are two good reasons. I give you others, but that's probably enough.
Well, just not catching fire is a great enough reason as it is. Thank you for your answer. So my next question is directed to Dr. Rojas. So the question is, how do you test for space environments?
So that's a good question. And you know, as we move with this renewed interest in space applications and you know, the commercial side of things taking off. So the main test we do is thermal vacuum chamber. So we care about materials outgassing. That's one big issue. But also, you know, the thermal aspects of it, or you can do environments from minus 80 C to 200 C. So we do that test in the lab with our collaborators, actually the lab next door. We do thermal vacuum chamber. Vibration testing is also another test we do, just to make sure that the device will survive the launch environment. And then we are developing a ionizing radiation test setup to test mostly shielding, additive manufacturing of packaging for radiation shielding. So that's being set up with a collaborator here at Embry-Riddle. The one test that is hard to do on ground is the atomic oxygen, which is you can find in the LEO environment. And really the only way you can do it, or you know, perhaps the one way you can do it is you go into the International Space Station and setting up an experiment outside of the International Space Station, for example. And then you can see how the materials degrade there. So that's one way to test for a space environment.
Thank you, Dr. Rojas. So my next question is directed to Dr. Sigmarsson. And the question is, how can one avoid cracking while drying the printed ceramic suspension?
So that's a major open question, really. You have to do with time and temperatures and things like that. So I mentioned earlier that when drying tape, it's dried for potentially days. Whereas if we're trying to rapid prototype something, we don't want to print one layer and then dry it for you know, hours and hours. But you know, so these are kind of open questions that we still need to address. The one potential is to combine convective heating and maybe some optical heating, maybe either laser or yeah, we might even start trying to do some direct sintering of the material itself. So that's a very good question, and it's a big challenge. And what we've had happen with a lot of the stuff that we've printed is if you dry it too quickly, it will crack, and if you dry it not enough, when you build the next layer on top, it will crack. So there are a lot of open-ended questions there, but it is all about the trade-offs between heat and time. So
I appreciate the answer. My next question will be directed towards Dr. Armiento. The question is, you had mentioned tailoring ink/paste feedstocks for RF applications. Is UMass Lowell also doing this type of research with loaded thermoplastic feedstocks?
We haven't been actively involved with that. We've discussed it. We don't have, we do have the capabilities on the campus to do filament extruding. In fact, UMass Lowell has one of the only plastics engineering departments in the country. You know, the challenge with that is those systems are made for industrial extruding, which means it requires a lot of volume, and which typically doesn't work for us. So we're talking about getting a small filament extruder so we can start to do that work, because the work we've done on the BST, ferroelectric ceramics in ink form, some work had been done with my colleague Alkema Kirtlu and Professor Joey Mead for Netflix project on actually putting that into substrates. So there is precedent for incorporating things like the BST nanoparticles into other materials, but we haven't really pushed it into filament form yet.
Excellent. Thank you so much for your answer. I'm going to jump back to Dr. Sigmarsson. We have an attendee question in regards to your RF switch design. The question is, could you explain about the process more, and is it additively manufactured?
So I'll answer the latter question first. Yeah, the goal is to completely print it or completely additively manufacture it. And the idea would be to build it up layer by layer and ideally include it into the printed ceramic process. But if we were just wanting to print a switch, you really need a few different things. You need a conductive trace, of course, and then you need some kind of an actuation method. And in the example that I showed in the slides, we would print a heater element or some kind of resistor that we would print underneath the phase change material, and then by applying electrical excitation to it, we would heat and change the phase of the material itself. So effectively what we would be doing is, if you think of a transmission line with a block of material that either is going to be conductive and therefore shorting to ground, or it would be dielectric and therefore just slightly changing the impedance of the line, but still allowing the energy to pass through. So hopefully that answered the question. If it didn't, feel free to email me and we can take this offline.
Thank you. Let's jump back over to Dr. Waxman. It's a loaded question. So the first part is, what is the benefit of additive manufactured batteries? And the second is, what are the additional features you would like to see in additive manufacturing equipment for this specific application and any others in that matter?
So the first advantage is the ability to control the architecture. And that's what we were doing with that modeling work. Right now, batteries are made by random structures. Typical batteries actually sort of the reverse of what we do. They have a cathode or anode particles, and then a liquid electrolyte then fills the space between those particles. It's a very random porous structure. We're doing the exact inverse of that. We are making an electrolyte structure, which is porous, and then filling the particles into the space between them, the cathode or anode material. By additive manufacturing, we can control that architecture. So for example, the thicker the electrode is, the higher it is, the more energy density you have in that battery. But the problem is, if you make it really thick, it's very difficult to get the current through it. So you have to design the structure so that the ions and electrons are running perpendicular to the interface. How large of diameter do they need to be? What's the spacing? Things of that nature. We can adjust those features with additive manufacturing, therefore, to address the trade-off between energy, which again is how long your battery lasts, and power, how fast you can charge and discharge it. The additional feature I'd like to have, I would love to be able to have a controlled environment 3D printer, because lithium does not like moisture. Actually, I should say first, lithium likes moisture, but the battery doesn't like moisture. And so I need to have a dry room environment around the printing. So to the extent that I could get an in-script that will allow me to have a controlled environment where I could dehumidify the internal part of that chamber, that would be awesome.
We'll definitely start working on that for you, Dr. Waxman. Thank you for your answer.
Sure.
I'd like to jump back to Dr. Rojas. And my question is, printed antenna on conformal surfaces like UAVs, if they are made of metal, are there antenna designs that can work on metal substrates?
Yes, definitely, yes. So actually, you can leverage the metal, as part of your design. Sometimes, depending on the type of antenna you're doing, a large metal ground plane might be useful. But at the end, if you have, you can make your antenna design kind of independent of the back of the substrate below the, the structure of the UAV by doing multi-layers, as you saw. So what we do multi-layered electrical conductive layers, and the other presenters also do the same. So the answer is yes, you can design for that, and you can make a multi-layer structure that makes the antenna kind of not affected by the structure of the UAV.
Excellent. Thank you so much. So I will jump back to Dr. Armiento. And my question for you is, you'd mentioned the importance of dimensional control on the printed Varactor. What is the range of dimensions, and how important is it to maintain control / repeatability?
Well, the dimensional control, I think I might have been referring to a printed resistor, which, our experience with some of the carbon inks is they're kind of viscous and hard to control their dimension, which is why we switched to the silver BST ink, because we know we can print that very accurately in our aerosol jet printer. So the critical dimensions for the dielectrics is often the thickness. I showed a quadrature coupler which had the two metal lines where energy coming in on the bottom gets basically coupled to the top, and there's a dielectric in between, and obviously the thickness of that dielectric, as well as its dielectric constant and its loss tangent, all affects that. So the dimensional control in the dielectrics is often mostly thickness, and especially for things like a coupler where it's just a critical dimension. And we're still struggling with how to print a good dielectric. We're actually doing some work on developing UV curable inks. We actually have a PhD chemist student working with us. We have a lot of material scientists in the group too. So our electrical engineers are learning a little organic chemistry. But it's kind of what you need in this industry right now, because the materials are so critical. You can't just have, a bunch of us double E's just playing around with stuff. We need material science and chemists to work on it. And particularly in this area of dielectrics, I think it's particularly an important need.
Excellent. Thank you. We'll shoot back over to Dr. Sigmarsson. The question is it possible to do in situ sintering of the LTCC materials as opposed to oven-based sintering?
And that's a good question, and kind of alluded to it a little bit in an earlier question. And in the past, we have used a laser, an infrared laser, to sinter LTCC materials directly onto a board, both conductors and dielectrics. So that's a very exciting thing to pursue, is to maybe even see if we can use one of the laser attachments to, like, the gantry unit end script, to see if we can directly sinter the materials as we're printing them down. And that would be a really exciting thing to try. And I definitely think we can do that. And based on what we've done in the past, I mean, we know it's possible. It's just, can we get the machine to do it? That would be the question.
So we only have time for a few more questions. So I'll hit one of the last ones with Dr. Waxman. The question is, can you provide your thoughts on printing millions of batteries, and also your thoughts on printing the batteries throughout a circuit to replace one large battery?
there are lots of applications for batteries from very small to very large. So, you know, I mean, this is probably a standard question people have for additive manufacturing, how fast that scales. Right now, we're looking at these for small batteries. And in fact, we're looking for the opportunity of printing batteries directly on chip carriers, the things that, you know, H was talking about, right? I could print a battery directly onto a ceramic substrate and put it next to all the integrated circuits. So that's one application. There's micro batteries, things of that nature. Consumer electronics, making batteries for cell phones and laptops, that's fine. If we start getting to automotive and grid scale, that probably is more problematic, just because the size of the batteries are required. So right now for me, this is more for the smaller scale up through consumer electronics. You know, so, but at the same point, we're looking using it as a tool to learn how to design batteries, and that goes back to the modeling work, and that type of understanding can be applied then to the larger batteries that are done for grid scale applications.
Excellent. Thank you. I will jump back to Dr. Rojas. And the question is, you had mentioned high K inks. Are you developing these materials, and can you discuss that development?
We are using commercial inks that are not used traditionally for additive manufacturing. They're used in different industries. So we're exploring them and characterizing them. So one of the issues I will mention with the high K inks is the loss tangent or the losses in the material. And so we are characterizing them as well and looking for the best candidates. So to answer the questions, we use commercial inks that are used in our industries. At the moment, we are not developing inks, the high K inks.
Okay. Dr. Sigmarsson, question for you is, how fast do you think the 3D printing of LTCC can be, and how does it compare to the traditional LTCC processing?
So the traditional LTCC processing takes, you know, with the sintering profile and everything, it can take a couple of days. Typical DuPont 951 tape process, if I remember correctly, is about 48-hour sintering process. The goal would be to try to leverage the capabilities of 3D printing to cut that time down drastically. I mean, I don't know if we could, in good conscience, call a 48 to 72-hour print job rapid prototyping, although we do. I mean, we do build multi-day jobs, but in general, if it's slower than the original, then I wouldn't necessarily call it that rapid. But I think with the addition of laser processing, I think we might be able to get it down faster, at least, than the traditional processing. So for the prototypes. So.
Thank you, Dr. Sigmarsson. And then we'll wrap it up with Dr. Armiento. So the question is, can you comment on how the biasing was done for the tunable FSS?
Yeah, we have a network of interconnections that feed the voltage through the unit cells, which are metal patterns. And it's not straightforward. I think to really be production worthy, you would need another layer of metal somewhere to feed those voltages in there. I would say, that requires a bit more development work, but you basically print another layer of bias lines on the structure.
I have one more question for you, actually. We had a attendee question last second. My question is to Dr. Armiento. Can he explain the performance of printed CPW?
Well, it depends on what you're talking about, right? We can do a fairly good job printing low loss CPWs on Kapton. But the work and we've got a lot of examples that I didn't show here, but the challenging one was to print grounded coplanar waveguides for connectors using extruded Ultim, right? So we start with, it's all done in our script system. You're printing Ultim. You're dealing with the surface roughness associated with any FDM printer. We're looking at smoothing techniques for that because that surface roughness can cause all kinds of problems. If you think about the surface of that ultim having slight pinholes and nooks and crannies, kind of like an English muffin, and then you're applying a conductive ink that seeps into those nooks and crannies, you no longer have a nice planar interface between the conductor and the dielectric, something you know. So those CPWs have more loss than we would like. And that's kind of the phase we're working on now, is trying to improve that. So if you're printing on an extruded 3D plastic, ultim or peak, that's an additional challenge that you're not going to see if you're printing on a CPW on a nice smooth piece of Kapton. Then you're mostly dealing with the fact that the conductor isn't as conductive as you would like, because everyone wants to compare it to a copper double-sided coplanar, a double-sided board, right? So that's what we're up against. And he's trying to give some of this stuff to a system guy who says, well, I can do better with conventional technology. That's the fight we always fight. And so our goal is to figure out how to change the form factor to let these folks do something they can't do with conventional materials.
Thanks, Dr. Armiento. That concludes the Q&A section. I'd like to thank all of you sincerely. You guys have been extremely cooperative with the Zoom and all the technical issues and everything else. You guys put on great presentations and had even better answers. You guys are truly changing the future of additive manufacturing and direct digital manufacturing, all of that. And you guys are disrupting the game. So you guys should all be proud of what you guys are doing. I'd like to send this back to my colleague, John Hornick, and he can wrap it up for us. Thanks, guys.
Yeah, I'd just like to echo what Brandon said. Thanks to all the speakers. You're really pushing the envelope of digital manufacturing. And also thanks to the audience for all the great questions. As I mentioned, these webinars, last week's webinar and this one, are available on the Nscript website and also on YouTube. Everyone take care and stay healthy. Thanks. Bye.
Thanks a lot, everyone. Appreciate it.